Hello everyone, welcome to this video lecture on sequencing problem part 2. In this video lecture we are going to discuss about n jobs through more than one machine problem, that is n jobs through 2 machines problem, 3 machines problem and m machines problem. In the previous video lecture we have discussed about the n jobs through one machine problem. And here we are going to discuss about problem with n jobs through more than one machines. Here there are some terminologies used. First one is job. The jobs are items, are customers, are orders, are the primary stimulus for sequencing. There should be a certain number of jobs, say n, to be processed or sequenced. And next terminology is number of machines. A machine is characterized by a certain processing capability or facilities through which a job must pass before it is completed in the shop. It may not be necessarily a mechanical device. Even a human being assigned with jobs may be taken as machines. There are certain number of machines, say M is to be used for processing the jobs. So n jobs, m machines. And next is processing time. Every operation requires certain time at each of the machine. If the time is certain, then the determination of the schedule is very easy. When the processing times are uncertain, then the schedule is complex. Next comes total elapsed time. It is the time between starting the first job and completing the last one. Idle time, it is the time the machine remains idle during the total elapsed time. Technological order. Different jobs may have different technological order. It refers to the order in which various machines are required for completing the job. Example, here you can see there are 4 machines, M1, M2, M3 and 4. A job is required to start from the machine M1, then it should pass to M2, then to M3, and then to M4. This order in which the jobs will be processed is actually known as technological order. Here it is M1 to M2, to M3, to M4 and finally finish. And there is something called as no pausing rule, which is applicable in sequencing problem. It implies that pausing is not allowed. That is, the same order of jobs is to be maintained over each and every machine. If each of the n jobs is to be processed through m machines in the order of M1, M2, M3 and M4, then this rule will mean that each job will go to the machine M1 first, then to M2 and to M3 and finally lastly to M4. No job is allowed to pass any machine. That is the meaning. Then there are 2 different arrival patterns. One is static arrival pattern. That is, if all the jobs arrive simultaneously, it is called a static arrival pattern. Another one is dynamic arrival pattern, where the jobs arrive continuously. These are all the terminologies used in sequencing problem. Next comes the basic assumptions related to sequencing problem. No machine can process more than one job at a time. That is the first assumption. The second one is the processing times on different machines are independent of the order in which they are processed. Next is the time involved in moving a job from one machine to another is negligibly small. That is, there is no transportation time available. So if it is given as processing time, it also includes the processing actual machining time and the transportation time between one machine to another machine. So it is assumed that time, that is transportation time from one machine to another machine, is actually considered as very small, that is negligibly small. And each job once started on a machine is to be performed up to the completion on the same machine. All machines are of different types. All jobs are completely known and are ready for processing. A job is processed as soon as possible, but only in the order specified. If it is M1 to M2 to M2, M3 to M4, then it should be processed only through the same order. These are the assumptions which is to be considered to make the sequencing problem a simple one. Otherwise, it is very, very complex and it will be complicated to solve also. Next, we are going to discuss about processing of n jobs through 2 machines. So, there will be only 2 machines and there may be unlimited number of jobs. So, there are n jobs available and only we will be having two machines, that is A and B, and all the jobs should be processed in the order of A and then to B. Right? That is, each job should go to the machine A first and then to machine B. That is, no passing rule is applied here. No passing off is not allowed. And here A1, A2 up to AN and B1, B2 and up to BN will be the expected processing time of n jobs on these 2 machines, that is machine A and machine B. By having this, yes, we are going to solve this sequencing problem by using Johnson's algorithm. These are the steps of Johnson's algorithm. First thing is we have to find out the smallest processing time in the total list of machine A and machine B. Right? After finding out the smallest processing time, if it is on the machine A, we have to place the particular job at the first place, and if it is on the machine B, we have to place the particular job at the last. After just placing it in the particular place, then we have to cross off that job. And while selecting the smallest processing time, if there is a time, right, and that processing time, if it is if the one of the processing time on the machine A and another one is on the machine B, what we can do is we can easily schedule the job with the least processing time on machine A first and on machine B at the last. But if there is a tie for minimum on the same machine, say machine A, then we can select any one arbitrarily and we can choose any of the machine at the first place and the second tie job in the second available position, right? And if it is on the machine B, if there is a tie on the machine B itself, we can do the same thing. That is, we can choose any one and we can schedule it in the last available position first and then next is last available position. We have to repeat these 2 steps, that is step number 2 and 3, after deleting the particular jobs. Then we have to continue this process until all the jobs are assigned. So that is actually called as optimum sequence. After finding out this optimum sequence, what we have to do is we have to do 2 things. One is we have to find out the total elapsed time, that is the total time between starting of the first job and completing the last job on machine B. That is actually called as total elapsed time. We have to find out that. The next thing is we have to find out the idle time of machine A and machine B. Let me have an example. Here there is a question. In a factory there are 6 jobs to be processed, each of which should go to the machines A and B in the order of AB. Sometimes this may be given in reverse order also. We have to just see it very carefully. And the processing times in minutes are given. We have to determine the optimal sequencing and total elapsed time. Also the idle time of machine A and B. This is a processing time in minutes. We have 6 jobs, 2 machines, and the processing time in minutes are given here. We'll see how to solve this type of problem. So this is a given sequence, that is processing times. By having this, first thing is we have to choose the least processing time by considering all the processing time. The least processing time among this is 1. So this is on the machine B. If the least processing time is on the machine B, what we have to do is we have to schedule that particular job in the last available position, right? So 1 minute. So we have to schedule it in the last available position. So we have 1, 2, 3, 4, 5, 6 available position. This is actually optimum sequence what we are going to construct. So the minimum processing time is 1, which is on the machine B. So we are scheduling it in the last available position, right? The job number 6. Next thing is we have to just cross the particular job out. We should not consider it for allocating. So we have to cross it out. Next thing is in the remaining matrix, we have to look for the least processing time. The least processing time is 2 minutes now, which is on the machine A. If it is on the machine A, we have to schedule the particular job in the first available position. So first available position is very first position. So the particular job, which is number 3, is scheduled in the first available position. After scheduling this, we can just cross it out like this. Then in the remaining matrix, we have to look for the minimum processing time. The minimum processing time is 3, which is on the machine B. So it should be, if it is on the machine B, it should be scheduled in the last available position, right? So like this, the last available position is the 5th position. So job number 1, which is having the minimum processing time on the machine B, is scheduled on the last available position like this. Then we have to cross the particular job out. And in the remaining matrix, we have to look for the minimum processing time. The minimum processing time now is 4. Here there is a time, and one is on the machine A and another one is on the machine B. So it is very easy for us. So job 2, which is on the machine A, should be scheduled in the first available position, and job 5, least processing time on the machine B. So if it is on the machine B, we have to schedule it on the last available position. So 2 is on the first available position, 5 is on the last available position, like this, right? 2, 5, and the remaining one can be scheduled here, which is job number. Then we have to cross it out. Then the remaining is scheduled in the available position, like this, right? Now this is our optimum sequence, 3, 2, 4, 5, 1, 6. By having this optimum sequence, what we have to do is we have to find out the total elapsed time and ideal time of machine A and machine B. So this is how we have to calculate. First we have to formulate the table like this. This is a job sequence. This is optimum job sequence what we have found now. Then this is machine A and machine B processing time, which is given in the problem. We have to rearrange it according to the optimum sequence. Then machine A time in, time out. Machine B time in, time out. Idle time for machine A, idle time for machine B, right? So this all thing we have just found out the optimum sequence, and we all know the processing time which is given in the problem. So after this we have to start from this position, that is machine A time in. We have to consider time in as 0. Then what will be the time out? It should be 0 plus machine A processing time, which is 2. 0 plus 2, which is 2, right? Then after doing this, this is job number 3. Job number 3 first should be processed on machine A, then to the then it should be passed on to machine B after completing on the machine A. So the machine A completion time is at the end of 2 minutes. The same time it will be transported to machine B, and the time in on machine B will be 2, right? And the time out from the machine B will be what? 2 plus machine B processing time, which is 6. 2 plus 6 is 8. Right? Then the same way, then we have to come for the second job. Here the second job is job number 2. Job number 2 can be started only after after completion of the first job, which is job number 3. So time out for the job number 3 is 2 minutes. So at the end of 2 minutes, that is the 2 minutes will be the time in for job number 2, right? And time out for this job number 2 is 2 plus 4, which is 6, right? And here this job 2 should go to the machine B. It is available from 6 minutes, but the thing is the machine B is not available up to 8 minutes. So even though the job 2 is waiting from 6 minutes, it should wait up to 8 minutes to start the processing in machine B, right? So what we have to do is we have to consider these two numbers, that is time out on machine B and time out on machine A for the particular job, and whichever is maximum, it should be the time in for the particular job on the second machine, correct? So the time in will be 8, then the processing time will be 8 plus 8, which is 16, correct? Then the same way for the job 4, here you can consider the time out of machine A is 6. So that is time out of job 2 is 6. So from 6 minutes onwards, we can just time in the job number 4. So time in for the job number 4 will be 6, and the time out will be 6 plus 5, which is 11. And here also the same thing. This is the job 4 is available, but the machine B is not available. So time in for the job 4 will be 16 here. And time out will be 16 plus 6, which is 22. So same way for job number 5, the time in will be time out of the previous job, which is 11. And time out will be 11 plus 9, 20. And here the time out of the previous job, which is 22, will be the time in for this. So 22 plus 4, 26. Next comes job 1. Time in for the job 1 will be time out of the previous job, which is 20. And the processing time is 7. So 20 plus 7, 27 will be the time out for the job number 1. And here you can see that here the time out of the previous job from the machine B is 26. Even though the machine is free, but the job has to be processed in machine A first, then only it should come to machine B, right? So here it is available from 26 minutes, but the job is available only from 27 minutes. So the time in for the machine B for the job 1 will be 27. That is, we have to consider these two values, 27 and 26, whichever is maximum we have to choose it, right? So it is 27 will be the time in for the job 1 in the machine B, and time out will be 27 plus 3, which is 30, right? Next for the job B, here the time out of machine A is for the previous job it is 27. So the time in for this particular job number 6 is 27, and the processing time is 8 minutes. So 27 plus 8 is 35, which is the time out for the particular job from machine A. And the time in for the machine B will be this time out of machine A of the same job, which is 35, because it is available from 30 minutes, but the job is not available. So the machine has to be idle for some time, right? So this is 35 will be the time in for the job 6. Next, the processing time is 1. So 35 plus 1 is 36, Right? This is how we have to calculate the machine A time in and time out and machine B time in and time out for all the jobs. Now we have to find out the idle time for machine A. Just consider only the machine A values. Here the machine A is starting from 0th minute, then it is going on processing 0 to 2, 2 to 6, 6 to 6 and 11, 20, 27 up to 35 it is working without taking any idle time. But the total elapsed time, that is, what is the total elapsed time? The time between starting of the first job in the first machine and ending of completion of the last job in the last machine. That is actually total elapsed time. So 36 is our total elapsed time. So the machine A is busy up to 35 minutes and it is idle only for 1 minute. That is 36 minus 35 is 1. That is the idle time of machine A. Here, how we have to calculate this is out time minus in time. This difference is the idle time. So 0, 0, 0, 0, 0 and here it is 36 minus 35. So it is 1 minute is the idle time of machine A. The same way we have to calculate the idle time of machine B. Here the time in of the first job is 2 minutes. So from 0 to 2 minutes it is idle time for the machine B. That's why it is given as 2 minutes idle time for machine B here. Then after starting it is working up to 8, then 8 to 16, 16 to 16, 22, 22, 26, 27. Here there is an idle time of 1 minute. Time out of the previous job is 26. Time in of the present job is 27. So here there is a 1 minute idle time. That's why it is specified here. So 27 minus 26. The same way here 35 minus 30 which is 5 minutes. So this is also an idle time of machine B. So after computing all these details, we have to take the results out of this table. So total elapsed time is this one 36, that is time out of the last machine, that is last job from last machine. So 36 minutes is the total elapsed time and idle time for machine A is the totally 1 minute and idle time for machine B is 2 plus 1 plus 5 which is 8 minutes. So this is how we have to calculate the total elapsed time, total idle time of machine A and machine B after finding out the optimum sequence for the particular problem. So next comes processing n jobs on 3 machines. Actually, yes, before that there will be n jobs and there will be 3 machines like this A, B and C. And all the jobs should be processed in the same order, that is A, then to B, then to C. No pausing of jobs is permitted and all the actual processing time in all the 3 machines are known. The problem is again to find out the optimum sequences which minimizes the total processing time. And this is how it will look like. There will be n number of jobs, 3 machines and the processing times will be given. And there is some conditions to be satisfied. Actually, there is no general solution available at present for this type of cases, that is 3 machines problem. However, the previous method, which is actually a Johnson's algorithm, can be applied if one of the following 2 conditions are satisfied. So let me discuss about that 2 conditions. First thing is we have to find out the minimum of AI, that is minimum of all the processing time in the machine A, that is the first machine. Then we have to find out the minimum of all the processing time of the last machine. Then we have to find out the maximum of the middle machine, right? For the first and last machine we have to find out the minimum processing time, and for the middle machine we have to find out the processing time of maximum processing time, right? After that is finding out all these three data, we have to check whether any one of the condition is satisfied or not. First condition is minimum of the first machine should be greater than or equal to maximum of the middle machine, right? And the second condition is minimum of the third machine should be greater than or equal to maximum of the middle machine. So if you want to apply the Johnson's algorithm, the same procedure what we have seen up to now, the one either of the conditions should be satisfied. At least one of the two conditions should be satisfied, right? If it is not satisfied, we couldn't have any method to solve this type of problem. The particular method fails to proceed, and no other solution procedures available at present, right? Okay, so this is for 3 machines problem. If you have m number of machine also, multiple number of machine also, the same condition will be applied. That is, what we have to do is we have to find out the minimum value of the first machine, the same way minimum value of the last machine, and maximum value among all the middle machines. If you have 5 machines in total, if you just leave first machine and last machine, we will be having 3 machines. We have to look for the maximum value among all the 3 middle machines, right? And the same condition should be applied, and any one of the condition is satisfied means we can just proceed with the Johnson's algorithm, alright? So after satisfying one of the conditions, we have to go for one more small procedure before applying the Johnson's algorithm. So if you have only 2 machine only, we can obtain the optimum sequence, right? So first thing is we have to convert the given problem into an equal problem which is having n jobs and 2 machines, right? That 2 machines which is fictitious will be called as G and H, right? We'll see how we can calculate the processing time of G and H machine. That is, if there is a 3 machine problem, first we have to add the processing time of machine A and machine B, and we have to have that processing time as machine G's processing time. That is first machine and the middle machine, right? At the same way, we have to add the middle machine and the last machine's processing time and have it as H machine's processing time. So we can convert the 3 machine problem into 2 machine problem only to find out the optimum sequence, right? And if it is an m machine problem also, the same thing can be done. That is, we have to convert m machine problem into 2 machine problem. We will be having only G and H machines. That is, we have to just ignore the last machine and add all other machines processing time. That will be G machine, right? That is, first machine plus all the middle machines processing time will be added to get the processing time of G. The same way, for getting the processing time of H, we have to add all the middle machine's processing time with last machine processing time, just only leaving the first machine's processing time. We will be converting m machine problem into 2 machine problem, and then we can just proceed as such, right? So we can apply the same procedure what we have used for 2 machines problem to find out the optimum sequence, which also will be optimal for the original problem. Whether it is a 3 machine problem or m machine problem, it will be the same. Okay, we will solve a problem. A machine operator has to perform 3 operations: turning, threading and knurling on 3 machines A, B and C in the order of A, B, C. A, then B, then to C. Find the optimum sequences when the time in hours are given. So we have 6 jobs, 3 machine, and the processing times are given. What we have to do is, first we have to check the conditions For that, we have to find out the minimum processing time in the machine, the first machine, which is 2. Then maximum processing time in the middle machine, which is 8. Then minimum processing time in machine C. So minimum processing time in first machine and the last machine, maximum processing time in the middle machine. Then after finding out these 3 data, we have to check whether at least one of the condition is satisfied or not, right? The first condition is minimum of this should be greater than or equal to, right? It should be greater than or equal to. Greater than or equal to this one. Here, it is not satisfied. It is 2, which is a very less value as compared to 8. So, the first condition is not satisfied. The second condition is minimum of C machine should be greater than or equal to maximum of the middle machine. So, it is equal. So, the second condition is satisfied. So, we can proceed with the Johnson's algorithm procedure. Right? So, to find out the optimum sequence, first we have to convert the 3 machine problem into 2 machine problem. So, this is a given problem. First we have to find out the G machine's processing time and H machine's processing time. So, if you just add first 2 values, that will give you the processing time of G. 3 plus 8, 11. 12 plus 6, 18 and so on for all other jobs. For getting the processing time of H, we have to add the last 2 machines. That is the last machine and the middle machine. So, 8 plus 13, 21, 6 plus 14, 20, 4 plus 9, 13 and so on for all other jobs. So, now we have converted 3 machines problem into 2 machines problem. This is only to obtain the optimum sequence, right? So, by having all these processing times, we have to obtain the optimum sequence as usual. So, this is the converted problem. Now, we have to look for the least processing time. The least processing time is 8, which is on the first machine. So, we have to schedule the particular job number 4 in the first available position. Right? So, this is optimum sequence. So, we have scheduled it in the first available position. Then, we have to cross off the particular job. Right? Then, in the remaining matrix, the minimum is 9, which is also on the first machine. So, the particular job number 3 should be scheduled in the first available position. Like this. Right? And we have to cross it out. And in the remaining matrix, we have 11. We have 2 11s, one on the machine 1, another on the machine 2. So, machine 1 job should be scheduled in the first available position. Machine 2 job should be scheduled in the last available position. So, first job number 1 should be here and job number 5 should be in the last available position. Like this. Then we have to cross it out like this. Then in the remaining matrix, the lowest processing time is 12. So, it is on the first machine. So, it should be scheduled on the first available position. That is job number 6 should be positioned here. Like this. And in the remaining should be scheduled in the remaining available position like this. Right? So, this is how we have to find out the optimum sequence 4, 3, 1, 6, 2, 5. By having this, we have to find out the time in and time out for all the 3 machines by having the original processing time. Then we have to find out the total elapsed time, idle time of machine A, machine B and machine C. So, these are all the values which is given in the original problem, and this is the given sequence. So, this is actually the optimum sequence what we have found in the last slide. This is actually the first machine, which is a turning machine, second is threading and third one is knurling machine. Time in, time out for all the machines is given here. Time in for the first machine is 0 And the time out for this is actually job number 4. Job number 4, machine 1 is require 2 hours of processing, 2 hours or whatever may be the time unit. It required 2 units of time. So 0 plus 2 will give you 2. This is a time out, right? So the time in of the same job on the second machine will be 2, and for the threading operation, that is second machine operation, for job number 4 it requires 6 hours. So 2 plus 6 is 8. This is a time out. Then 8 will be the time in for the knurling operation of the job 4. For the job 4, the knurling time requirement is 12 hours. So 8 plus 12 is 20. Right? So the first job is over. For the second job, the time in for the job number 3 is the time out of the previous job on the same machine, which is 2. And the processing time of this is 5. So 2 plus 5 is 7. And here the time in will be the maximum of the time out of this job in the first machine, and time out of the second machine of the previous job, right? Because even though the job is available from 7 time units, but the machine is available only from 8 time units, right? So the timing for the third job will be 8. And the processing time of this is 4. So 8 plus 4, 12. And here the timing will be 20. And the processing time is 9. So 20 plus 9, 29. The same way we have to calculate the time in and time out for all the jobs on all the machines, right? After if you have any doubts, just pause the video for some time and just look each and every time in and time out. Then it will be very clear for you. After calculating all these things, right, we have to calculate the idle time. Here, the starting from 0 time units, it is very busy. 2, 7, 10, 21, 33, up to 42 time units. But the total elapsed time is 77. So the idle time of turning machine, that is the first machine, will be 77 minus 42, which is 35 time units. Alright. For the threading machine, the starting time, that is 0 to 2, it will be idle. So 2 units will be the idle time for threading operation here. And after this, 8, 8, 12, 12, 20, 21. Here there is 1 time unit idle time. Then 22, 33. 33 minus 22, that is 11 time units the idle time of threading machine here. Next, finally, the time out of the last job from the threading machine is 45. But the total elapsed time is 77. So this before that there is some more some 3 time units, that is 39, 42 minus 39. This is the idle time of the machine here, and that should be added with this. That is the difference between 77 and 45. 77 minus 45, which is 32. 32 plus 3 is 35, right? These are the idle time. And here for the knurling machine, it is 0 to 8 time unit, that is 8 time unit will be the idle time at the starting, then 20, 29, 42, 55, 69 and up to 77 time units it is busy. So these are all the idle time. If you just sum it up, we will be getting the total idle time of all the machines. So from this table we can just get the details of total minimum elapsed time is 77 minutes if we just follow this optimum sequence for these 3 machines. And the total idle time of turning machine is 35 minutes. And the total idle time of the threading is 35 plus 11 plus 1 plus 2, which is 49 minutes. Next idle time for knurling machine is 8 minutes. These are all the solution what we can just get it from this 3 machines problem. Thank you for patience hearing. In the next video lecture, we are going to discuss about graphical method of solving 2 jobs problem by having M machines by using graphical method. Thank you for patience hearing. Thank you.